Okay, I actually decided to split this lecture up into two lectures. And so now, after talking about the texture of igneous rocks, we're going to move on to the composition of igneous rocks. Composition referring to what something is made out of. So, as a little bit of a hint or just a cheat, when we think about the composition of igneous magmas or rocks, what we really need to remember is, or ask ourselves, is where did the magma come from? And we've talked about this already in our prior units on plate tectonics and minerals. For the mantle, when magma originates from the mantle is richer in magnesium and iron. And so we want to carry that piece of information forward with us when we think about igneous magma and rocks. If the magma, though, comes from the crust, the continental crust, to be more specific, remember that it is going to be richer in silicon and oxygen. Those are the two most abundant elements in the continental crust. So we need to think about the plate tectonic settings that will draw our attention to magma from the mantle or to magma from the continental crust. And then we want to tie it in with these specific elements. Okay, so with that information, the composition of igneous minerals can largely be broken into two categories. The first category is called mafic. It's shown here on the left. These minerals that then go into the formation of rocks tend to be darker in color. They can be black, dark gray, or even green. These these minerals that lead into rocks tend to be richer in iron and magnesium. So I hope that you're already cueing in on the piece of information from the last slide. The types of minerals that we can find for this category are black mica, biotite mica, pyroxene, amphibole, and olivine. We've already talked about olivine several times. It's that green one. Great. Okay, so then the second category, the felsic. Felsic minerals, then leading to felsic rocks, tend to be lighter in color, light gray, white, maybe even translucent, and sometimes even pink or red. These elements, or these minerals, tend to be richer in silicon, aluminum, sodium, calcium, and potassium. Silicon is the one I really want you to pay attention to. The different minerals that tend to be most common are muscovite, feldspar, and quartz. We've seen quartz before. It's that translucent one. So we can look at the different minerals, say in the silicates that we learned about in the last unit, and we can start to categorize which of these minerals belong to mafic categories of minerals or to the felsic category. So olivine, we already mentioned, that dark green mineral, that is clearly going to be mafic. Pyroxene, again, rich in iron and magnesium, mafic. Amphibole, iron and magnesium rich as well, mafic. Now, down here, when we get to the biotite, biotite tends to have more iron and magnesium, so that one is mafic. But there is the muscovite, which is clearer, or white mica, and it is very rich in silicon and oxygen, as well as potassium and aluminum. So this one is felsic. So there's one variety of this mica that is mafic and one variety that is felsic. And then plagioclase. This plagioclase is rich in silicon, oxygen, aluminum, and potassium, so that's felsic. And then quartz is basically just silicon and oxygen, so that is clearly felsic. So we've taken the minerals that we learned about previously, and we're starting to see that certain minerals tend to lend us towards mafic category. Remember iron and magnesium. And then the other minerals tend to lend us towards the felsic category. Remember silicon and oxygen. So then this generally leads us to three dominant categories. On the left here, we have felsic. And that is the light minerals rich in silicon and oxygen. And then on the right, we have mafic, and those are the darker minerals rich in iron and magnesium. And in the middle, we have a category that's a little bit of a blend of both, the intermediate. So here is just showing you that there is a spectrum, a transition from light minerals to dark minerals, and the proportion of elements like silicon and oxygen and iron and magnesium. As one goes up, the other goes down. So for felsic minerals and felsic rocks, we have high silicon and oxygen and low iron and magnesium. It's not totally devoid of those. It's just lower in proportion. And then on the flip side, mafic has low silicon and oxygen, not zero, just low, and high iron and magnesium. And so these are on a continuum that we transition to depending on the situations and the characteristics that define these rocks. Okay, so this is the complicated chart. You should probably take a minute and pause right here just to study this a little bit. I'm going to break down this table so you can see the information and what it's trying to tell you. Down here, we have those three different categories. And there's actually a fourth category called ultramafic. It's just like even more iron and magnesium and even less silicon and oxygen. I think you get the idea. So compositionally speaking, we have these four different categories that we're familiar with now: felsic, intermediate, mafic, and ultramafic. As we go to the right side of this table, we can see those minerals that are most often associated with that category of composition. So we said that the composition of felsic is most often found with quartz, hydroclase, and orthoclase. This is completely different from those in the mafic or the ultramafic category. On the mafic and ultramafic category, we are dealing with things like olivine, pyroxene, those really, really dark minerals. Now, in the middle of this table are some names that you probably are not familiar with, but I wanted to give them to you because they really have a lot of meaning behind them. The headers, the titles of these columns, though, those should be familiar to you by now. On the second column, this left one, we have aphanitic. We've heard that term. It is a fine-grained texture, the very tiny minerals formed by extrusive volcanic eruptions. So for this one, we have rhyolite. This is a felsic composition that was erupted as a lava. Rhyolite is the name that we give to that. If, however, that magma remained inside the earth and never erupted onto the surface, it would crystallize and cool down to have a phaneritic texture, very large minerals, through the intrusive magma chamber, and that would form a granite. You've probably heard of granite before, but you might not have known that it is really only limited to those rocks that are those magmas that are felsic in nature, rich in hydrogen, silicon, and oxygen, and that cooled slowly inside the earth. This is an example of a granite. Getting down here, we can see other names like basalt. Basalt is the mafic variety of lava that is put down onto the surface of the earth. If that lava never makes it to the surface, that magma never makes it to the surface, and it stays inside of the earth and cools down, we would then have a gabbro with very large minerals. This peridotite here, this ultramafic, the formation inside the earth, cooling slowly, really nice olivine crystals. That is what you see here in there. And then intermediate as well, forming large crystals. This is a diorite. So this table, although there's a lot of information, it's really easy to break down once you know the various categories of composition and the different categories of composition, and then things related to texture and what minerals might be found there.